I don't know.
I worked on the new one the other day. And
You would at least be able to execute it in one of the, I don't even know what to call them, one of the virtualized devices. You know, so if I'm going to run Packet Tracer on this box, I load it on the virtualized version of that box just like I would do it on the hardware. Whether it will run under the hood of that and see the view of the whole thing, I don't know. I kind of doubt it. Man, think about the processing it'd have to have. Okay, so for both the local and the online class, of course, I've posted the project. My goal in the project, let me preface this with a couple of thoughts. I am not asking you to go through and do lots of math calculations on path loss or that sort of thing. This is simply an extension of the discussions we've been having. Always catch me by surprise when that thing chases. This is simply a discussion of what we've been doing. It's obviously a more complex environment. I've given you very simple geographic coverage problems. I've given you very simple number of users problems. We've complicated that more by having geography that has unevenly distributed users. We complicated it further by having to do multi-layer, multi-floor buildings and that sort of thing. This is simply a yet more complicated problem. You have the same sort of things going on. I have limited the choice of antennas to 90-degree sector antennas or omnis. I have limited you to 1, 6, and 11. And my goal in this is I want you thinking through how you look at the physical layer design, because that's really what we're talking about here. We're not doing protocols at this point. Physical layer design for delivering services to users. I admit the way you typically do this with this hardware is you take your best guess, put it out there, and let the automatics take care of assigning channels. That's great. I look at that kind of like I look at spanning tree protocol. It's foolish to not run spanning tree, but it covers a multitude of sins if you don't. You can use it to not do good network design. You know, hook everything up, turn on spanning tree, let it decide where the traffic goes. I want to decide where my traffic goes. And so that's the same approach I'm taking here. I know the automatics work, but I think you end up with a more stable network if you do the design and think through what you're doing with channel assignment, what you're doing with coverage, all of those physical layer things we've been talking about. So that's my goal in this. In this problem, we are looking at the Curris Center. Some of the online class may not know. Curris Center is a student center here on campus. It's a pretty good sized building, 3 stories. It's poured concrete, oddly shaped spaces. You can tell from the designs and everything. And what I want you doing is thinking through what we have control of. What realistically, when we choose a Cisco access point, which is what we're using because that's what the university uses. When we choose that, that decides really what the power capability is, right? Because whatever the manufacturer builds, that's what I can do. You can assume that any AP you buy will meet those sort of minimum performance requirements for 802.11. It's a LAN, it's a wireless LAN, so we generally think of it in free space being able to cover about a 300-foot distance. So I can have a user about, and I'm being purposely vague, about 300 feet from an AP in free space. Last time I checked, we weren't walking around in free space down here, so you're probably going to get something approaching that. We're going to go into how the protocol does that in the last week in here. But for now, I want you thinking about how the reach of these APs can work in a building. You may assume that 300 feet is adequate to cover the whole area of the building. That's not our problem. Our problem is we have concentrations of users. And we have some odd ones. And we also have to provide coverage for the whole public space of this building, 3 floors worth of it, for a very highly variable load. You know, you walk around in the Curris Center right now, there are probably not 30 people in the public spaces of that building. Go in at lunch, go in when they're having one of the special events they have over there, go in when they've got a group up on the 3rd floor using the ballrooms, and you can have 200 or 300 people in those public spaces. And we have to think through that kind of design. What I did with the first part of this just tells you, I limited you to the 3 channels, so you have to think about channel design. I limited you to the 1, 6, and 11 because that's still the world that you're going to play in. For a while, there are going to be more users at 2.4 than there are at 5.8, where we have lots of non-overlapping channels. So I'm making you deal with that. I've basically taken away the choice of frequency from you. Okay? You can assume, as I just mentioned, you can assume that any single AP can cover any of the areas we have to in that building. Now, a question came up from one of the online students earlier today about what do we do about walls? You know, how much does that reduce signal coverage? I can't give you an answer for that. I know it reduces it. We're using free space path loss. What is free space? Not the equation. We defined what free space is. What is it? I'm sorry? Distance and frequency are the variables in the equation. But when we say free space loss, what do I mean by free space? Not even open air. You're right. Open air, but not even open air. We're talking about space, no matter. In free space, the only signal degradation is because of dispersive loss, that inverse square law expanding wavefront thing that we looked at a long time ago. And the only variables on that, as you mentioned, are the frequency of the signal, which I've locked you into the frequency range here, and the distance. You may assume, since we're talking about a product designed to cover 300 feet, that it will cover 300 feet in free space. What's going to happen when I put that inside a building and we're not in free space anymore? What's going to happen? It's going to do somewhat less. But these products are designed to work where we are most of the time. So what I'm trying to get you to do is think through how bad that change in range is going to be. If I take one of these APs and I put it out in the middle of a relatively open area, say one of the walkways through the middle of campus, it's going to perform one way. If I put it inside a building, like this building right now, it's going to perform another. This building, for whatever reason, is unusually absorbent for RF. I have, near the corner of my office, less than 70 feet from my office, a full commercial grade Cisco AP, and it can't push a signal into my office. You walk through my office door and the signal disappears. So those are the kind of things you run into. How do you deal with that? To be honest, if you were doing a design for a building like this, you did the best you could on paper, but before I spent the money to buy 10 or 12 or 15 $800 APs, I'm going to buy a couple of them, I'm going to mount them temporarily, and I'm going to walk around and see just how good my coverage is. It's called heat mapping. There are applications for it, and it basically is a glorified way of measuring signal strength. It does it graphically. We'll talk about it. We'll actually, I'm trying to arrange for us to look at it. So what I'm wanting you to do on this project is just think through that kind of installation. You don't have control over frequency. You have control over power, but realistically what that means is you can reduce power to cover smaller areas. That's the practical value of being able to do that for us. Okay. The other control you have is the choice of antenna pattern. Where am I going to put energy? Well, if I'm trying to provide service to people, I need to put the energy where those people are. And I don't need to put it where the people aren't. Okay? And that it's this wide, it's this high look of the world is really what I'm wanting you to do on this. I'm not after a 7-page write-up on this. I am literally wanting you to copy these shapes and do the kind of thing we've been doing in this class. Tell me where you would put them. Tell me how you would assign channels. Identify issues. You're going to have some. You know, with 3 channels, you cannot do this without having some co-channel adjacencies. You got to do the best you can, but you need to identify those issues for me. Okay. If you, well, I won't give you a length on this. I am more interested in you thinking through the solution on this with those variables than I am this big in-depth write-up. Okay. 2 heads ups. You are not trying to guess what Lamar did. That's great. Lamar's going to come in Friday and tell us what he did. An online class, I will post that for you on Monday because that's when your project's due. You're not trying to guess what I would do. I want you to think through this with your understanding. This is kind of the last shot we're going to take at this one. So if there's something you don't understand about this discussion, now's the time to come up with it. Okay. First floor on the building, I think I pretty well outlined that. Basically, you have a lot of space that's cut up in smaller, cubicles and stuff. Not a lot of people. The public spaces are over here. You have a big area that's commonly used, rented out and used for gatherings or special events or something. This is an area that is used by students in the public. These are guest rooms. I'm sorry, these aren't the guest rooms. These are offices and such. Second floor, and that's what all this is. It just kind of identifies the load, the people load and all that.
The door on the left?
This one?
Yeah, that's the door to the parking lot.
Yes. Door to the parking lot to the north. I identify by the room number on this how many people you have in there. When I say public spaces, I'm meaning all this open space. The first floor doesn't actually have a lot of open space down there. You can pack more people in there, but generally you see a lot of people on the second and third floor. Second floor, big areas here. This is the cafeteria, the dining area. So, you can put 250 or 300 people, I forget what I said, 375 in there. You have food prep areas back here. Probably not going to have a lot of folks, but you'll have some. You have the university store in this area, post office, back rooms, all that sort of thing. And you have lots of public space out here. Lots of it. So that shows in the way the people are distributed. Third floor. Third floor has offices for the Curris Center staff. It has guest rooms for overnight accommodations for speakers and stuff like that. The biggest thing is it has several meeting rooms that are used. Okay, these are the big dining hall kind of meeting rooms. The Curris Center ballroom. So when they have an event, you can have a lot of folks in there. I don't know what the legal capacity is, but I'll bet it's about 400 to 500. We have a theater in here that seats, I think, 200 people in there, some thereabouts. And I've indicated that with the piece with the numbers down here. So what I'm asking you to do is think through how you would solve covering the geography and serving that number of users. One change is that the Cisco APs, as Lamar mentioned, don't have the 25-person support. The particular one we looked at support 128 clients. Okay. Yeah, it makes it with the 25, with the numbers there and 25 users per AP, you would basically just cover the ceiling with APs. Yeah. So 128 clients on those. Were it me, I'd make it 125 to make the math easier, but that's me. Okay. Anything in particular you want to discuss? Again, this is getting you to think. Ideally, I would give each of you 10 APs and a controller and let you go make your own solution over there. I can't do that here or at the online class. So what I can do is give you a real-world problem, let you work through what we've discussed in here, and then talk to the people that are actually doing this, actually running this network. Yes, sir?
Lamar talks about high school kids coming in there.
Mm-hmm.
So are we going to do something for Jet?
What he was talking about was how it is actually higher up in the protocol stack. At this point, I'm just wanting you to deal with physical coverage. Okay, how do we cover the geography? How do we provide service to that number of users? We're not worrying about different networks yet. Okay, good question though.
You just want an explanation underneath each floor?
Yeah, come in. So here's first floor. In here, you're going to run into another page behind this, certainly. And I want to know if you take those shapes and you figure out your coverage here, why did you do it the way you did it? What was your thinking? What are the problems that you see with your solution? There will be problems. Nothing in this is perfect. So what are the problems that could potentially be something that you have to deal with your solution? Okay. And just do that for each one. I'm sorry?
Can we put APs anywhere?
Yeah. Yeah, you may assume that you can put APs anywhere. Again, something that Lamar would probably be jealous of. Yes?
What was the distance on the panel antenna?
You mean coverage distance? I can't answer that. You are taking. I'm not being a smart aleck. The way you think about that is realize what's going on. An Omni, of course, has 360-degree coverage. I'm taking 3/4 of the energy. I'm taking all of the energy and squeezing it into 1/4 of that space. So it's going to propagate. It's going to be able to push a signal further. You're still dealing with, that's where that inverse square loss comes from. So would it go 4 times as far? No. Might go twice as far. I would probably, I would accept 600 in this class, yeah. My guess is probably not. You'd probably do between 450 and 500 reliably. But for this class, yeah, you can think double. You're welcome.
You said that we could assume that one AP, if that was free space, it could cover it all.
Yeah, I mean, the current center is less than 300 feet in its longest dimension. Okay, so you can assume that one AP could cover that whole area, but just from a point of view of being able to push energy. Okay, again, that's probably on the edge of being real, but for what I'm wanting you to think through, that's an okay assumption. I'm fine with that. Okie dokie. We'll see you guys Friday. Stop.